Hi everybody, we are getting close to the end as we start section 13.3, which is arc length and curvature. And so we've talked about arc length before in chapter 10, both polar and parametrically, and so this is going to look a lot like that parametric type stuff that we were doing back in chapter 10. So if you remember back in section 10.2, we did the arc length formula as this formula up at the top, where we did the square root of each derivative squared added together, and then you integrate that. Well, the length of a space curve is defined the exact same way. Since we're going to do a 3 space, though, we'll have to have a derivative for the x, the y, and the z, all underneath the radical, and then integrate that. Sometimes you'll also notice that there's a more compact form, that the length is this box over here, where we have the norm of the derivative of our vector function r. That's just the same way that the other formula is. Most people don't remember that one. Usually, since we already talked about it in chapter 10, most people go off of this one over here on the bottom. That's what I'm going to use as well as we go through the next few problems doing the arc length. So let's find the length of the curve given the vector t, 3 cosine t, and 3 sine t between -5 and 5. So we just jump in with our formula, and we say that the length of the curve would go from -5 to 5. That's our distance it tells us to work with. And we do the square root of each derivative squared. So the t, the derivative of t is 1. Derivative of cosine is negative sine. So I'll get a negative sine t with the 3 on it, squared. And the derivative of a sine is cosine, dt. And then from there, it's just ever how you remember how to do integrals from Cal 2. This is 1 plus 9 sine squared plus 9 cosine squared. And so what I automatically notice is that we have an identity sitting here. I can factor the 9 off of the sine and the cosine part, and I'll have sine squared plus cosine squared. And so since that identity is 1, that part just goes away. I just get 1 plus 9 times 1 dt, which is the square root of 10. So the square root of 10 could actually be pulled out in front of my integral, and I'm just integrating dt. Or just 1 dt if you want to look at it as a 1 dt. So I just get t between -5 and 5. So that would be 5 minus -5. Plugging it in for the t for the 5 and the -5. So 5 minus -5 is 10, so I get 10 root 10. And that would be the length of my curve. So that's a fairly easy one, so hopefully that's not too terribly bad. I'll show you one a little bit more complicated than that. All right, let's do the same thing. Find the length of the curve. Here, now we have root 2 times t, e to the t, and e to the negative t on the ij's and the k's. We're going to integrate this thing from 0 to 1, because that's the interval it tells me. And I'm going to do the square root of the derivative of the first one. Well, the root 2 is just in front of the t, so the derivative of the t would go to 1, so I just get square root of 2 squared. E to the t doesn't change when you take its derivative with respect to t. And e to the negative t will pick up a negative in front, like this. And so I'll get 2 plus e to the 2t and then the positive on the negative on the e to the negative t getting squared will become a positive, but the power will stay negative, so this will become e to the negative 2t. Now, here you have to just notice what this is, because it just, you're going to have to be able to recognize what you would do at this point using your Cal 2 skills. One thing I would point out is that you might want to rewrite it in a different order. That might help. So I'm going to put it in this order: e to the 2t, 2, and then e to the negative 2t. That actually factors. This is probably not one that you would normally just recognize that would factor, but it's technically the first term squared, the second term squared, and you multiply them together and double it, and you would have the middle term. And so this is really e to the t plus e to the negative t all squared. It is a perfect square trinomial. It's just not using x's. It's not x squared or y squared or some other letter. It's using exponentials. But it factors the same way. And that's good, because then the square root and the squared cancel each other, just to give me e to the t plus e to the negative t. Positive here, since we are not actually solving an equation, and because you're going to plug positive numbers into it anyway. And so these are both really easy to integrate. E to the t doesn't change. E to the negative t would be e to the negative t divided by negative 1, which would be negative e to the negative t, between 0 and 1. So my length of my curve would be e to the 1 minus e to the negative 1 minus e to the 0 minus e to the negative 0. Well, e to the 0 is 1, and e to the negative 0 would also be 1. So these last two terms actually cancel each other off. And you're left with e to the 1 is just e. E to the negative 1 is 1 over e, so you could do 1 over e, or you could leave it as e to the negative 1, whichever one you want to do. But that would be the length of your curve. Now, there are a lot of functions that you just can't integrate, and you're just going to have to do some sort of decimal approximation for as well. So sometimes you'll get to a point and be like, I don't know what to do. So let's look at one like that. Find the length of the curve to 4 decimals. Now, usually I would, if we were doing on a test or something, not make you find the decimal approximation. It would be more like just set it up, but don't worry about it. And so I'll kind of show you what that looks like here. Now, we do have 2 points given, not the t values. So you have to figure out what 2 values for t gives you these 2 points, and that would be your interval. What I would look at for the easiest thing would be this 2t right here, based on the 0 and the 4. So that looks like if you use t was 0, 2 times 0 would be 0. And if you use t being 2, 2 times 2 would be 4. You can plug those in on the other ones to be sure. That would be correct. So we're actually going to go between 0 and 2 for your t values. And so then we just go to the formula and see what we can do. So the length of your curve would go from 0 to 2 of the square root of the first one's derivative. So cosine goes to negative sine. Since there's a pi in there, I'll pull off that pi for the chain rule. The 2t, its derivative will just be 2. And the sine 2t pi would be kind of like the first one. Sine goes to cosine because of the 2 pi. You have to do the chain rule here. So if you do wanted to go one other step and square the things out, this would be pi squared sine squared pi t plus a random 4 plus a 4 pi squared cosine squared 2 pi. And that would be setting it up. Now at this point, because the cosine squared doesn't match with the sine squared, they have different arguments. One has a 2 pi. Oop, I left the t off, didn't I? Look at the t right there. It's a 2 pi t versus a pi t, so they don't match. There's not a 4 in common you can factor off. There's not a pi squared in common you can factor off of everything because of the 4 in there. So you're kind of stuck. And so at this point, we would go to some sort of computer-aided software, whether that be Mathematica or just a really fancy graphing calculator would work as well. But if you were to type this in and get a decimal approximation, it comes out to about 10.3311. But if I was to ask you on a test, just set it up but don't actually work it out, I would do the step before that and say that's as far as we're going to go. Okay, the next little topic in here about beyond arc length is what's called curvature. And so our r of t, or in fact, sorry, this actually should have been a bold r because it's a vector, but our vector function rt is called smooth on an interval if your derivative is continuous and your first derivative is not 0. So there's no sharp points, there's no cusp. This would be kind of the same idea if you went back to Cal 1 and looked at what the definition of differentiable was. Differentiable means that if you took your derivative, it was continuous. Well, this is the same sort of idea. And if your curve is smooth, then your unit tangent that we've talked about before indicates the direction of the curve movement for the curve C. And then the curvature is how fast the curve changes. So it's kind of like the derivative a little bit. So there's 3 different definitions given. You could say that the curvature, and it looks kind of like a K. It's not officially a K. It's a fancy scripted K, but if you just put a K, it's fine. The curvature, it could be the magnitude of the unit tangent derivative. That's that first definition. Or the one over the little box on the right hand side, it is the magnitude of the derivative of the unit tangent divided by the magnitude of the derivative of the vector. Or, a little term at the bottom, the curvature is also given by the cross product between the first and second derivative divided by the first derivative's magnitude cubed. That's usually the one most people use, is that bottom one. So most of the time we're going to be going with this one. There's actually one more formula. I might show that one along the way too. So let's find the curvature. If I'm given a vector r as root 6 t squared I plus 2tj plus 2t cubed k, well, what I could do is do the formula where I'm going to do the cross product and then divide it by the magnitude cubed. So I'm going to do that formula. To do that, I have to first find my derivatives. So my r prime would be 2 root 6 ti plus 2j plus 6t squared k. Just power rules all the way across. And then r double prime would be just 2 root 6. The t goes away. There is no j term anymore then, and 6 times 2 makes 12 t k. And so I have to do the cross product between these two vector functions. So I want to do r prime crossed with r double prime. And I'll have an I, a j, and a k. And then I'll do the 2 root 6 t, left the t off there for a minute, a 0, and then a 6t squared. And then on the last line, I'll have a 2 root 6. Oh, sorry, I put the 0 on the wrong one, didn't I? This one's not 0. That one is 2 because there's a 2 in front of the j on that one. There's a 0 on the second one. And then a 12t. So for the I, you would end up with a 2, a 6t squared, a 0, and a 12t on the I. On the j, you would have the 2 root 6t, 6t squared, 2 root 6, and 12t on the j. And then on the k, you would have the 2 root 6t, the 2 root 6, and the 0 to get the k. And so my cross product would end up being 2 times 12 will give me 24t, and 0 times 6t squared is 0. On the j, 2 root 6 times 12 would be 24 root 6t squared, because they both had a t on them, minus 6 times 2 would give me 12 root 6t squared on the j. And on the last ones, I'd have a 0 minus 2 times 2 is 4 root 6 on the k. So it's looking like we're going to end up with a 24t on the I. 24 minus 12 would give me 12, but it's got a negative in front, so I get a minus 12 root 6t squared j. And then I'll get a minus 4 root 6k. And at this point, you really pray that you didn't miss a sign up or something along the way. Then my formula for my curvature, maybe I'll do it in green. And like I said, it's a k, but it's a kind of a weird looking k. I have to do the magnitude of the cross product. That's why I got to start with finding the cross product, divided by the magnitude of the first derivative cubed. Now, it's a lot better when you have numbers to work with, but we don't have any numbers here. So the magnitude of the cross product would be take each one of those terms and square it that I just found. And by the way, a lot of times this does not simplify very well. So I left the negative off the 12. And then I have a negative 4 root 6 squared. And that's going to get divided by the magnitude of the original r up there at the top. Oh, sorry, the r prime. The 2 root 16. The 2. And the 6t squared. And that whole thing has a cube on it. Don't that look nice? Yummy, yummy, yummy. So 24 squared is 576. For those of you who don't know off the top of your head. The root 6 squared would be 6. The 12 squared is 144. So you're doing 144 times 6, which is 864 times t to the 4th. And then again, the root 6 squared would be 6. 4 squared is 16, so you get 16 times 6, which is 96. All divided by. On the bottom, this one's a little bit easier. 2 squared is 4 times 6 is 24, so I get 24t squared plus a 4 plus 36t to the 4th. And that whole thing on the bottom, this whole bottom, is cubed. Now, if you would like to leave it like that, that is perfectly okay with me. You could do a lot of algebra a lot of algebra, and it does simplify. If you factor out the right thing, there's a 96 in common on top, there's a 4 in common on bottom. Then you could get it down to perfect squares that you could cancel the perfect squares off. You could get this thing down to the square root of 6 on top, and you could get it to 2 times, no radical here, just 3t squared plus 1 squared, if you wanted to do all the algebra. I would not. I would stop right here and call it a day. But some of you might like algebra and I might like a challenge. So if you want to try it, see if you get the same thing I did. And hopefully I didn't make a mistake along the way simplifying that. Okay, this one also says find the curvature. But please notice there's a number, 111. Putting numbers in makes everything work out much nicer, and it's a lot easier to simplify. And so at the point 111, we'll have to figure out what the t value is. Hopefully it's kind of obvious. If they all come out to be 1 and the first one has a t by itself, that t must obviously be 1. So that's the value we're going to work with. I do need to find its derivatives and things. So the first derivative would just be 1, 2t, and 3t squared. The second derivative will be 0, 2, and 6t. So when I do my cross product, since I'm finding it at the point, I could go ahead and plug that point in and actually do the cross product, evaluating each one of them at 1 instead of at t. And so I'll have an I, a j, and a k. But for the first row, I'll have 1, 2, 3. For the second row, I'll have 0, 2, 6. And those numbers I got from plugging this t value into both the r prime and the r double prime. And then it just makes it so much easier to work with numbers. So your I will use the 2, the 3, the 2, and the 6. The j will use the 1, the 3, the 0, and the 6. And the k will use the 1, the 2, the 0, and the 2. And so I'll get 2 times 6 is 12, minus 2 times 3 is 6. 1 times 6 is 6, and then 0 times 3 is 0. 1 times 2 is 2, and 0 times 2 is 0. So I'll get 6i, a minus 6j, and a 2k. Or if you want to write it in the same format, this is 6, negative 6, and 2. And that would be my cross product. Then for my curvature would be the magnitude of my cross product evaluated at 1 divided by the magnitude of my first derivative evaluated at 1 all cubed. So I need to do the magnitude of the cross product. Well, that's fairly easy now because I just got numbers in here. This is 6 squared, negative 6 squared, and 2 squared. On the bottom, I'll have, plugging in the 1 in, I'll have 1, 2, 3. So I'll have the square root of 1 squared, 2 squared, 3 squared. That whole thing gets cubed. And so on top, I get a 36 and a 36 and a 4. Now, it may not come out very nicely, but at least the numbers are better. On the bottom, I'll get 1, 4, and 9. So 36 doubled is 72. So 73, 74 times 76. On the bottom, 4 and 1 make 5, and 9 make 14. So that doesn't come out terribly good. Not awful, but not, I mean, it could have been better, right? 76 does simplify. If you do want to simplify it, it is 19 times 4. So it's 2 root 19 if you want to simplify it. And this is 14 root 14. So you could cancel the 2 and the 14 and make it root 19 over 7 root 14. Or, you know, some version of that. Or if you want to rationalize it, you could keep going and multiply the 14 on the top and the bottom and simplify it. But it actually doesn't matter. So any of those numbers across the bottom there, the last 3 or so, would be sufficient for the answer. Okay, like I said earlier, there is one other type of formula that if you don't have it in parametric terms, you could do the curvature based on a different formula. That's this formula here. Not very popular, but I thought I'd show you one example of it. Find the curvature for just y equals x to the 4th using this formula. And so we're going to do the second derivative of x, or the second derivative of the function y x to the 4th. And then we'll have a first derivative on the bottom down there. So those are pretty easy derivatives to come up with. Your first derivative is 4x cubed. Your second derivative is 12x squared. So our curvature here would be using the second derivative on top. So I have the absolute value of the 12x squared divided by, in the bracket, 1 plus, my 1 looks a lot like an L. Let me get that part off. 1 plus the first derivative, which is 4x cubed, all squared to the 3/2. Now, luckily, 12x squared, the absolute value of 12x squared will be just 12x squared, because if you square something, it'll be positive, and multiplying it by the 12 would be positive anyway. So on top, I'll just get 12x squared. On the bottom, I'll end up with 1 plus 4 squared is 16. 3 times 2 gives me 6 to the 3/2. And that's it. That's about all you would do, unless you have a number to plug in. Or if you want to write the square root of all that stuff cubed, pretty much like what you would have seen. The 3/2 power is the same thing as the square root cubed, so it's kind of like the same denominator from the previous one. Okay, here's one of the things that kind of makes people wonder why they're doing this course. When we talk about finding different vectors. So at a given point on a curve, as long as it's a smooth curve, no jumps, gaps, breaks, whatever, there are many vectors orthogonal to the unit tangent. But the principal unit normal, or just the unit normal, is one of those vectors that we would like to know something about. And so the unit normal would be n, which would be the first derivative of the unit tangent divided by the magnitude of the unit tangent. So I drew this little picture over here on the side, and you'll see there's a fuchsia circle going around. The curve itself is the green curve, so the line going up and down. That curve, there's a point on that curve, and it's got 3 vectors coming off of it. The red one going straight down, the blue one going off to the left, the purple one kind of going up towards the point. This point in the middle of the circle is actually the center of that circle. And so as this point moves along the curve, the unit normal would be the purple one. It points to the center of the curvature, which is that black dot in the middle, the center of the circle. The red line going down is the unit tangent. That is the vector that's tangent to the curve. And then we also have what's called a unit binormal vector. So the unit normal you can think of as indicating the direction to which the curve is turning. And so as it's turning, it's pointing that direction. The unit binormal, or just the binormal vector, is the one that is perpendicular to both the unit normal and the unit tangent. And it is also a unit vector because it is the cross product of two unit vectors. And so you cross the t with the n to find the b. And so we're going to, I'm going to show you how you can find these, hopefully, with not that much trouble. So we're going to start with this one that has lots of different numbers in it, which is kind of nice. Find the t, n, and b, the unit tangent, the unit normal, and the unit binormal at the given point. So again, it'd be nice to know what t value that would be. And so my t value, in this case, hopefully you can kind of tell that your t would be 1. 1 squared is 1, gives you the first term. 2/3 times 1 cubed would be the 2/3, and especially because of the last one just being a t, t would be 1. And so that is the t value we're going to work with. So I got to find the unit tangent. So the unit tangent, that formula, is the derivative of the r that you're starting with, divided by the magnitude of that. And so you could do this with just numbers, or you could do it with plugging the actual functions themselves in. I will have to do it with, at least this part right here, I have to do it with the function, because of when I find the unit normal, I have to use the function for the t to find the n. So at this point, I'm going to have to do the functions themselves. And so my derivative would be 2t, 2t squared, and 1. And then I would want to find the magnitude of that vector on the bottom. So I would have a 2t squared, a 2t squared, and a 1 squared. And so on the bottom, I'm left with a 4t squared, a 4t to the fourth, and a 1 underneath. Now that actually simplifies because that is a perfect square, which is nice. This is 2t, 2t squared, and 1. This bottom factors as 2t plus 1 all squared. Oh, sorry, I left the squared off. 2t squared plus 1 all squared, because you got to get to a t to the fourth. And so the square root and the squared cancel each other. So this gives me just 2t squared, and 1 divided by 2t squared plus 1. That would be my unit tangent vector. Now in this case, since t is 1, you can go ahead and plug that in. And so t of 1 would be 2, 2, 1 divided by 2 times 1 squared is 2 plus 1, which is 3. So I'll get the vector 2/3, 2/3, and 1/3. 2/3, 2/3, 1/3. But like I said, I have to do this in a generic version for this part because of my unit normal vector. My unit normal vector is the derivative of the unit tangent vector divided by the magnitude of the unit tangent. Oops, sorry, I left the derivative off. The magnitude of the unit tangent vector's derivative. And so at this point, I need to figure out how do you take the derivative of this thing that I have up there. Remember, the 2t squared plus 1 is just a function of t. And the thing on top is a vector. And I have a rule for derivatives using vectors in the previous section that said if you have a function times a vector, you can do the product rule. You cannot do the quotient rule. There is no quotient rule there. So I am going to have to rewrite this thing as 2t squared plus 1 to the negative 1 power times 2t squared, and 1, so that I can do the product rule correctly. Oh, sorry, the product rule. Okay, so the numerator here. The numerator is the product rule. So I would do the first one the way it is, 2t squared plus 1 to the negative 1, times the derivative of the second, which would be 4t and 0, plus the second one, the way it is, 2t squared, 1, times the derivative of the first one, which would be negative 1, times 2t squared plus 1 to the 1 last power times the derivative of the inside. And that would be the top part. Divided by the square root of for the magnitude of all that stuff up above it. So I'm going to kind of cheat here. It's the magnitude of this stuff. And you say, well, why are you going to do that? Well, because you have an option. You can simplify this thing with all these t's in it, but I know t is 1. So if I plug the 1 in there, it might simplify a lot easier. And then I could use the 1 for the magnitude for the bottom. So we're going to do, what is the magnitude at 1? So that would be this stuff. So if I plug 1 into that top part, I'll get 2 times 1 squared plus 1. That is 3. Times the vector 2, 4, 0. Then I'll have the vector 2, 2, 1. That negative sign, that minus 1, could make this positive in front, a negative. Then I'll have a 2 times 1 squared is 1, plus 2 is 3. So I have a 3, the negative 2, times the 4. I'm not going to touch the bottom yet, because I want to try to make the top as nice as possible. So the 3 to the negative 1 is 1/3. So I'll have a vector that is 2/3, 4/3, 0. 3 to the negative 2 is 1/9. So I have 4/9 times this vector. So that would be 8/9, 8/9, and 4/9. So if I subtract those things on the top, 2/9, or 2/3 minus 8/9. 2/3 is 6/9 minus 2/9. Oh, sorry, all the numbers running together. 2/3 is 6/9 minus 8/9 would be negative 2/9. Four thirds, which would be 12/9 minus 8/9, is 4/9. And then I have a negative 4/9. Now, for the bottom part, if I was to plug 1 into the, I left the primes off over here. If I was to plug in the 1 into the derivative part, I would end up with this -2/9, 4/9, -4/9. So I need the magnitude of that vector that I just finished finding. And so I'd have the square root of -2/9 squared, 4/9 squared, and -4/9 squared. One thing you could have also done is factored out the 1/9 and the 2 if you wanted to, and just put it out front. But it doesn't really matter. You'll get 4 over 81, 16 over 81, and 16 over 81. 16 and 16 make 32, and 4 more make 36. This is 36 divided by 81. The square root of 36 is 6. 81 is 9. So I would end up with 9/6 times -2/9, 4/9, and -4/9. Which simplifies, the 9 on top cancels all the 9s all the way across, and -2 divided by 6 is -1/3. 4/6 would be 2/3, and a -2/3. That is your n evaluated at 1. So if you have the n and you have the t, then you do the cross product to find the b. And I'll actually do that on the next page because I'm kind of out of room on this one. So to find that n vector, oh sorry, not the n vector, the b vector, or unit binormal, I don't need the generic version of each one, because since I'm doing it at a certain point and I have the vectors at that point, I could do that the binormal vector evaluated at 1 is the unit tangent vector evaluated at 1 crossed with the unit normal vector evaluated at 1, and I don't have to do all the t's and stuff for this version, which is kind of nice. And so we're just going to take all those 2/3 and 1/3 and things that we found on the previous two and do the cross product. And so I will do the cross product with the I, the J, and the K. My unit tangent was 2/3, 2/3, 1/3, 2/3, 2/3, 1/3. And my unit normal was -1/3, 2/3, and -2/3. And so my cross product will look like this. My I will use the 2/3, the 1/3, the 2/3, and the -2/3 on the I. The J will use the 2/3, the 1/3, the -1/3, and the -2/3. And the K will use the 2/3, the 2/3, the -1/3, and the 2/3. And that's a lot of fractions, so I'm hoping I'm not going to mess these up. So you'll get 2/3 times -2/3, which is -4/9, minus 2/3 times 1/3, which would be 2/9. On the J, you have 2/3 times -2/3, which is -4/9. And then you'll have a 1/3 times a 1/3 that is negative, so we'll have a -1/9. And then you'll have 2/3 times 2/3, which is 4/9, minus -2/9. So this is -6/9 I. -4/9 plus 1/9 would be -3/9. Positive would make a, or positive because of the minus sign in front, so I get a +3/9. And 4 and 2 more make 6, so this is 6/9. Okay, which of course those would simplify. -2/3, 1/3, and 2/3 if I wrote it in the other notation. So I get a negative 2/3, a 1/3, and a 2/3. That would be my unit binormal vector, which direction you're going away from the curve, perpendicular to the other two. So hopefully that's not too bad. Okay, let's try one more of those, and then we'll be done with, basically done with this section. So find the vectors t, n, and b, the unit tangent, unit normal, and unit binormal at the given point. Here, my t value, to get sine t to be 0, that means that t was 0. To get cosine to be 1, that means t was 0. And cosine of 0 is 1, so the natural log of 1 is 0. So yeah, t is 0 here in this case. Starting with the t's. And just like I mentioned before, you got to do at least this one in a generic version so that we can figure out what it is for the product rule to find the n, if need be. So the formula is the derivative of the vector r divided by the magnitude of the vector r, of the derivative of the vector r. And so across the top, the derivative, cosine goes to negative sine, sine goes to cosine. The natural log of cosine t, that's usually one that most people don't remember very well, but remember, if you have a natural log, you could always just put the denominator as what's inside the logarithm, and the derivative of that on top. So derivative of cosine is negative sine. This is actually negative tangent. So its derivative is negative tangent t, which actually works really well here because when I do the magnitude on the bottom, because they all have trig functions in them, this is going to simplify really nicely. So on the top, I'll have a negative sine t, cosine t, and negative tangent t. On the bottom, what I'll end up with is sine squared plus cosine squared. These are 1. But then I'll end up with 1 plus tangent squared. So that 1 plus tangent squared gives me secant squared. Or, since I'm doing the square root of that, I'll just get secant. So I'll get negative sine over secant. I'll get cosine over secant. And I'll get negative tangent over secant. But all of these simplify kind of, well, not terribly well, but they do simplify a little bit. Secant is 1 over cosine, so if I flip that over, I actually get negative sine times cosine on the first one. I'll get just cosine squared on the second one. And then flipping that over, you'll get tangent times cosine, which is sine. So that's my generic version here, which looks a little bit nicer. If you plug the 0 in, t at 0 would be sine of 0 is 0, so the first one goes to 0. Cosine 0 is 1, 1 squared is 1, and sine of 0 is 0. So there's my vector t at 0. Okay. One thing that might be a little bit easier if you want to do this is that sine times cosine, you can make that an identity so your derivative for the next part wouldn't be quite so bad. This is negative 1/2 sine 2t if you would rather write it like that. I'm going to do that just because I don't really want to do the product rule. And so on my n vector, remember that's t prime divided by the magnitude of t prime. And I'm going to do the same thing I did in the last one. I'm going to work the top part out, figure out what that vector is, and then do the magnitude of that for the bottom. And so t prime, cosine goes to sine. Sorry, I said that backwards. Sine goes to cosine when you take its derivative. The 2 would come out in front, and so I'd end up with 2 cosine 2t. Cosine squared, that's a power rule problem. You pull the 2 down, leave the inside the way it is, and multiply it times the derivative of the inside, which is negative sine. And then the negative sine t, sine just goes to cosine, and so you'll just end up with negative cosine t. So this is negative cosine 2t. The second one, 2 times sine times cosine, is also sine 2t, so this could be negative sine 2t and negative cosine t. On the bottom, you get the magnitude of that. And since it is trig functions, it might simplify, but there's a good chance that it won't, because one of them is sine 2t and the other one is just a t. And so we're going to do the magnitude of all this stuff up here. But I'm going to go ahead and just plug numbers in. So n, evaluated at 0, would be plug 0 into that top vector I just got. Cosine of 0 is 1, so I'll get a negative 1. Sine of 0 is 0, so I get a 0. And cosine of 0 is 1, so I get a negative 1 on top. And so instead of doing a magnitude with a bunch of trig functions in it, we're going to do a magnitude with a negative 1, a 0, and a negative 1. And it's a lot easier to say 1 plus 1 equals 2 than it is to try to do all those trig functions. So I get the vector negative 1 over root 2, 0, and negative 1 over root 2. That would be my unit normal vector. And then, like before, the cross product between the two give you the binormal. So I'm going to do that on the next page and cross them and see what b comes out to be. Okay, so my unit binormal vector evaluated at 1. I don't need to do anything in a generic format because I'm just plugging the 1 in anyway. Is the cross product, I guess I could write that part off again, since I put the formula on all of them so up to this point anyway. It is the cross product between the t and the n. So I'll have an I, a j, and a k. My unit tangent vector was 0, 1, 0. My unit normal vector was negative 1 over root 2, 0, and negative 1 over root 2. So the part with the I would use the 1, the 0, and the negative 1 over root 2. The part with the j would use the 0, the negative 1 over root 2, and the negative 1 over root 2. The fact that the top row is zeros probably says that this term is going to go away. And the part with the k's would use the 0, the 1, the negative 1 over root 2, and the 0. So I'm left with 1 times negative 1 over root 2, which would just be negative 1 over root 2, minus 0 times 0 is 0. I'd have 0 minus 0 on the j, so yes, that term does go away. And on the k's, I'd have 0 minus negative 1 over root 2. So I'm left with negative 1 over root 2 for the first component. The second component is 0. And the third one, the two negatives make a positive. And so I get a positive 1 over root 2. And that is my unit binormal vector to go along with my unit normal and unit tangent. So this last slide is just all the formulas in one place if you'd like to have all the formulas in one place. Nothing extra work-wise to do on this problem, just showing you that all the formulas all in one slide. And so that's the end of this section, and so we got one more section to go.